Okay, so in the last video we found that the Laplace transform of our function y, which is going to be our solution to our differential equation, very easy to lose track of what we're doing. We're trying to find a formula for y of t. Okay, the Laplace transform of it was this thing. And we said, I like that piece because that piece looks like that, so I can apply the inverse Laplace transform to get something that looks like that, just an exponential function. We said we didn't like these pieces because the denominators were more complicated. We said we needed to use partial fractions. Now, partial fractions gets introduced in second semester calculus. It's a great technique for integrating rational functions. So you do it a bunch in 3B, and then probably most of you haven't done it a whole lot since then. Even if you went through 3C, been trying to rack my brains, I'm not sure we ever actually needed to use partial fractions in any of the problems I assigned in 3C. I could be wrong, let me know if I'm wrong, but if we do need partial fractions, it's only once or twice. It's pretty rare, okay? The real main use for partial fractions is they show up all the time in differential equations, because we get things that look like this, and we want to make them things that look like this. Okay. So, some of you might say, oh yeah, I remember partial fractions, no problem, this is great. Others of you might say, oh, I haven't done that since 3B, don't really remember it. Think I remember that there was a thing called partial fractions. Okay, so what we're going to do is we're going to finish this problem using partial fractions. I'll just sort of do a quick review as we work through this problem. For some of you, that's going to be plenty. For others of you, you're going to say, gee, I got to go back and find my 3B notes and learn partial fractions again. The next video is going to be devoted to just a review of partial fractions per se. So for some of you, that's a video that you can skip if you feel comfortable with the partial fractions. For others of you, that's going to be a nice security blanket. It is coming. Okay, so I want to break this one up. So let's start with 1 over s plus 5 times s plus 1. Okay. I basically want to break that up into a sum of two fractions, one whose denominator is s plus 5 and one whose denominator is s plus 1. Okay. So I'm starting with this proper rational function, which means the degree on top is smaller than the degree on bottom. This would be degree 2 on bottom, because I've got an s squared on bottom, and degree 0 on top, because it's a constant. Okay, I've got it factored fully. Each factor is going to contribute a fraction to the partial fraction decomposition. Essentially, I'm saying, hey, this is the least common denominator that I would need to add two fractions that had these two denominators. And the rule is that if this denominator is linear, degree 1, or a power of a linear, so even if this was s plus 1 squared, the numerator is just going to be a constant. So there are two unknown constants, a and b, that are going to make this equation true all the time when it's defined, which would be everywhere except at -1 and -5. Okay. To solve for a and b, I'm going to multiply through by this least common denominator to clear all the denominators. So I'm multiplying this by s plus 5 times s plus 1, and I'm multiplying this by s plus 5 times s plus 1. Now when I do that, that just cancels the denominator here, so I just get 1. When I distribute that to this piece, the s plus 5 cancels, and I get a times s plus 1. When I distribute to this piece, the s plus 1 cancels, and I get b times s plus 5. Okay. Now, these equations are almost equivalent. This equation, we said, is true if s does not equal -5 or -1, because obviously that would make the denominators 0. Okay. All right, this equation, there's no way I could have a linear equation like this that's true everywhere except at two specific values. So this one is actually true for all s. By removing them from the denominator, I remove the fact that the equation isn't true at those particular s values. Okay. So I'm looking for the values of a and b that will make this equation true for every single value of s. That will be the same values of a and b that make this equation true everywhere where it's defined, which is everywhere except at -5 and -1. Knowing that this is true everywhere, I'm going to say, in particular, It's true if s is negative 1. And if I plug in negative 1 for s, that kills off the a's. So I get 1 is equal to b times negative 1 plus 5 would just be 4. So 1 is equal to 4b, and so b is 1/4. Now, I don't have to plug in negative 1. I could plug in 0. If I plug in 0, 1 is equal to a plus 5b. That's going to give me an equation in a and b. Plugging in another number would give me another equation. What's nice about plugging in negative 1 is it gives me enough information to solve right off the bat for b. So the other number that it's convenient to plug in is if s is negative 5. So if s is negative 5, this becomes 1 is equal to negative 5 plus 1 would be negative 4a. And of course, the negative 5 kills off the b's. So that's going to mean that a is negative 1/4. So I can now say we are getting negative 1/4 over s plus 5 plus 1/4 over s plus 1. Do just be careful. Whatever I called a is what goes over s plus 5. I don't get to just mix and match. A was the negative 1/4, that goes over s plus 5. Okay. So now I'm going to say this one fraction here that I didn't like becomes negative 1/4 over s plus 5 plus 1/4 over s plus 1. Now that looks a little bit messy because I've got fractions on the top, but essentially what's going to happen is I'm going to just say those fractions are just constants that I'm going to pull out and factor out. So totally fine that it looks kind of wonky at this point. Okay. All right, so now I just have to do the same thing for this fraction. Break it up into two fractions with simpler denominators. Okay, so 2 over s plus 5 times s. That was not a coronavirus cough. That was just me swallowing wrong. Okay, so I've got two factors here. Okay, and they're both linear. Okay. So each factor contributes one fraction to the partial fraction decomposition, and since they're both linear, the numerators are just constants. I could recycle the names a and b, but I'm afraid I'll look at where I wrote down that a was negative 1/4 and get myself confused. So I'm just going to use the names c and d. Okay. I'm going to clear the denominators, so I'm going to multiply both sides by s times s plus 5. So I get 2 is equal to c times s plus d times s plus 5. This equation is true for all values of s, including the two values that would make this equation undefined because they put a 0 in the denominator. So in particular, if s is equal to 0, I get 2 is equal to 0 kills off the c's, 2 is equal to 5d, and so d is equal to 2/5. If s is equal to negative 5, I get 2 is equal to negative 5c, and negative 5 kills off the d's, so that's going to tell me that c is negative 2/5. So my fraction becomes negative 2/5 over s plus 5 plus 2/5 over s. So now I can write this one as minus 2/5 over s plus 5 plus 2/5 over s. So this fraction became these two, this fraction became these two, and then I still have the one I liked, which is the 1 over s plus 5. Okay. Okay, so right now I've got 5 fractions. I think we can consolidate a little bit because 3 of those have the same denominator. So I'm just going to say I've got this one, 1/4 over s plus 1, plus this one, 2/5 over s, plus something over s plus 5. So let's see what I have. I've got basically on top, I'm going to have 1 minus 2/5 and minus 1/4. Those are the three numerators that I have. So let's see, that's 20 twentieths minus 8 twentieths minus 5 twentieths. So that's 20 minus 13 twentieths. That's going to be 7 twentieths. Okay, now each one of these is just a multiple of one of these guys. Okay. So that was my Laplace transform of y. Now I'm going to apply the inverse Laplace transform to both sides. So I get the inverse Laplace transform of the Laplace transform of y is equal to the inverse Laplace transform of 1/4 over s plus 1 plus 2/5 over s plus 7 twentieths over s plus 5. The Laplace transform and the inverse Laplace transform undo each other. That's just going to give me y. And I might actually write in, with y, we're back to being a function of t. This, oh my goodness, this is going to be the solution to that differential equation we started solving so long ago. Okay. Now here, I'm going to use the fact that the inverse Laplace transform is linear. And I'm going to go ahead and do this in one step. So I'm going to distribute it across the three pieces. And I'm going to take these fractions on top that are just constants and factor them out. So I'm going to have 1/4 the inverse Laplace transform of 1 over s plus 1 plus 2/5 the inverse Laplace transform of 1 over s plus 7 twentieths the inverse Laplace transform of 1 over s plus 5. Excellent. I am running out of space, so I think I'm just going to copy this up at the top, and we are almost there. So we've got y of t is 1/4 the inverse Laplace transform of 1 over s plus 1 plus 2/5 the inverse Laplace transform of 1 over s plus 7 twentieths the inverse Laplace transform of 1 over s plus 5. Okay, and I'm basically going to be using rule 1 3 times. I'm just going backwards. If this is the Laplace transform of that function, another way of saying that, and this is spelled out in more detail on the handout or the formula sheet, okay, is that this function is the inverse Laplace transform of that. Okay, so y of t is going to equal 1/4. This is 1 over s plus 1. S plus 1 would just be s minus a negative 1. So that's going to be e to the negative t. That was just formula 1, where a is equal to negative 1. Okay. Plus 2/5. This is 1 over s. That's 1 over s minus 0. So that's going to be e to the 0t. Now, I know that's actually just 1, and I'm going to simplify that in a moment. And it's totally fine if you went to just this is 2/5. Okay. I'm going to, just because this is still a little bit new, I'm going to go ahead and write the e to the 0t. Once we've done this 20 million times, I'm going to go straight to that's 2/5 times 1, which is 2/5. Okay. And then this is plus 7 twentieths. 1 over s plus 5, that would be s minus a negative 5. So that's going to be e to the negative 5t. And that's just formula 1, where a is negative 5. So my y of t is 1/4 e to the negative t plus 2/5 plus 7 twentieths e to the negative 5t. That is the solution to the original differential equation we had. Okay. So again, the next video will be sort of optional for some of you. I'm going to go over how we work with partial fractions. So just a reminder, in this one we had linear factors. We're also going to have to take a look at what happens if we have a repeated linear factor. So if I had something like s squared or s plus 5 squared, okay, And then we're also going to have to take a look at irreducible quadratics. That would be a quadratic that does not factor over the reals. So something like s squared plus 1, something like that. Or a repeated irreducible quadratic. Okay. So if you feel comfortable with partial fractions, or if you think you probably feel comfortable and that as those other situations come up, you'll just sort of see, no need to watch the next video. If you feel like you want to watch that to just review the algebra of the partial fractions, totally fine. I'll let that be your discretion.